Okay, today we will be using equation of statics and talking about variable acceleration to do a problem. In this case, our problem has to do with a fluid in which we're going to spin it at an angular velocity or rotate it at an angular velocity in a container. So our initial container is some water level over there, and when we spin it with a angular velocity, our tank is going to look like this with a water level right here, and it will look like that. So we're going to define a few variables, our first one being h, and our next one being large r, the radius of the container, and our h being the total height of the container. We'll assume that h equals r. I clicked something on accident. And then we will also assume that it is a cylindrical container. So what we're first going to want to do is relate the pressure with the change in pressure with the change in area, or the change in the radius. So we have dp over dr, and we know that the this will be equal to rho omega squared r, and the small r in this case is the specific r at some height of the fluid right here. So this is at some r and at some h right here. So that is a portion of our fluid once it's spinning in an angular direction. So now once we have this, we can multiply dr on both sides. So we have dp equals rho omega squared r, and our rho is the density of our whichever fluid we have in here, water, whatever it is. So now what we want to do is, we have dr over here. We can integrate on both sides. So integrate this side, and this would be from 0 to p. So assume that 0 and to p, and then we will make this side 0 to r, the radius of the container. So then we'll have our pressure is equal to, we can take rho out, the density times omega squared, angular velocity squared, and then this will be the integral of just from 0 to r of r dr. So then we know that this will be equal to rho omega squared times r squared over 2. So we can use this pressure equation, and we know that the basic equation of statics, P equals rho gz, or z being the height, so z is also h. We can use this to solve for h. So we know from this equation that h will be equal to omega squared r squared over 2g. So we will need to save this equation for later. And then we can also assume from this h, we can also assume that the h, the radius, the specific radius at the from the dip at some fluid equals the radius of the entire container, and we can say that this is also equal to omega squared r squared over 2g. Okay, so what we're going to want to do now is we're going to save this h, and we're going to use that to input into some of our other equations. But basically what we need to figure out now is, so we have our container right here and some initial liquid right here, and then when we start rotating it, it goes to this. Basically we need to figure out what is the distance from the bottom of the dip to the top of the container. So we're going to define that as d, and that d is at some volume right here. So basically we need to figure out what our volume is. So if we think about it, we can say that the volume of this right here is equal to pi r squared times the height. So we can say our volume is equal to pi r squared times d, and we are going to save this equation to input into our other volume equation here in a minute. So what we have next is basically, if we look at it, these two containers, I'm not going to draw them again, I'm actually just going to reiterate off these two pictures right here. Basically, you can think about it, there's some sort of volume right here. That volume, once you start rotating the container, goes up right here. But we can say that the volume of right here, between this little space of fluid right there, this is also D. We can say that that volume is equal to this volume. So using that information, we're going to set up an equation for a volume. So if we picture a container, again, we have our container right here, and we basically need to figure out over this area right here, what is the volume? So we can integrate and use our differential volume over this area. So what we need to do first is we can kind of think about it. If we look at the top of it, we can kind of think about if the water's spinning in a circular direction, it would look like a circle from the top. So we can say we can say that this is the area. So we can use the circumference of the circle times the height in order to get our differential volume, and then we can integrate that to solve for volume. So basically that's going to look like we're going to have a differential volume, the change in volume is equal to 2 pi r times the height. And like we defined up here, the height is equal to omega squared r squared over 2g. So we can put that into the equation as well. So this is a differential volume over some change in radius. And now we can move the dr to the other side, and we can separate and integrate both sides. So now what we're going to do is just have dv equals 2 pi r times omega squared r squared over 2g dr times r. And we're going to integrate both sides. This side being 0 to v, the total volume of the container, and this would be 0 to capital R, the total radius of the container. So this would be v, and then we equals, we can take the 2 pi out. The 2's actually cancel. We can just take the pi out, take the omega squared out, and take the g out. And then that will leave us with the integration from 0 to r of r cubed dr. And solving this, we have our volume is equal to pi omega squared over g times r to the 4th over 4. So now that we have this volume equation, this is the volume of this area right here. It's the volume of this right here. These two little sections of fluid when we have it spinning at an angular velocity. So that's what that equals to. And now that we have this equation, we can set it equal to our equation right here, our pi r squared times the height of the dip, and then we can solve for d and plug it into another equation we're going to talk about. So basically what we're going to do now is we're going to create another equation that we're going to use. So basically, like we said earlier, this is the total height of the container. This is the total radius of the container. We have the liquid fluid going like this. This is some specific radius of the container of the dip, and this is the height of that specific radius. It's not drawn very well, but you get the picture. So basically, we're going to relate the total height of the container with these other variables, and this will help us solve for the angular velocity at which the fluid will spill over the tank. So we're going to set h equal to large R, the radius of the container, minus the d, the distance of the dip in the top of the container, minus d, and then plus our height at some specific r when it's equal to the large R of the entire container. So that would be hr equals large R. So we're going to save this equation, and this will be the last equation we use in order to derive for the angular velocity. But first, what we're going to do is set our volumes equal to each other and solve for the height of the d, so the dip. So basically what we're going to do is we're going to take our pi r squared d right here and set it equal to our other volume equation right here. So we have our, I'm just going to create a separator right here. We have our pi r squared d, and we'll set that equal to our pi omega squared over g times r to the 4th over 4. So we can do some cancellations here. If we divide pi r squared on both sides, the pi cancels, this r to the 4th turns to r squared, this r squared cancels all the way, and we are left with our d equaling omega squared r squared over 4g. So now we have our distance of the dip before the fluid's about to spill out, and we can put it into this equation, and then we can isolate for our angular velocity, and this will give us the maximum velocity before the fluid spills out of the container. So we go h equals the volume of the radius of the container minus omega squared r squared over 4g plus, like we defined earlier, our small h, r equals larger r of the container, so our small portion radius at some height of the fluid is, we said earlier that this was also just equal to h, we assumed it, and then we said that this was equal to omega squared r squared over 2g when we derived that using the basic equation of statics with pressure. So we can say that is equal to the omega squared r squared over 2g, and now all we need to do is solve for the omega. So what we're going to do is we're going to move the h and the r onto one side, so we're going to have a negative omega squared r squared over 4g plus omega squared r squared over 2g, and that is equal to h minus r, the height of the container minus the radius of the container. So solving for this, we have omega squared r squared over 4g. All I did was cancel this 2 out and make it a 4. There's a 2 right here. A negative 1 plus a 2 is a 1. So we have omega squared r squared over 4g. And this is equal to h minus r. So now all we need to do is solve for our omega. So we have omega squared r squared equals, multiplied 4g on both sides, 4g h over h minus r. And then we have omega squared equals 4g h minus r divided by r squared. And then our last step is just to square root both sides. So square root. And we are left with omega is equal to 2 times the square root of acceleration due to gravity times the height of the container minus the radius of the container divided by some specific radius of the fluid when it's in angular velocity. So this will be our maximum angular velocity at which the fluid spills over the side of the tank. So thank you for watching this video, and hope you have a great day.